Today I want to talk about DeepSeek again. So why is DeepSeek good and cheap? So the first episode was about MOE, Mixture of Experts architecture. And the second episode is going to be about multi-head latent attention. So let's dive into it. Let me start with what is KV cache. So I have another Transformer episode, Transformer series, talk in details about KV cache. So please take a look if you want to know more details about it. But I will try to summarize it a bit. So KV cache is eligible when new token's attention's calculation only depend on itself and previous token, which is very normal for generative models nowadays. For example, the decoder-only GPT families. FYI, the diagram I put here is for transformer. It's encoder-decoder based, not decoder only. And the mask attention module here is what is critical for KV cache. It will make sure the token in a sequence only attends to previous tokens and itself, not future tokens. So what is the benefit of the KV cache? So it's going to drop the number of flops, floating point operation per second. It will drop it from OT squared to OT. So T is the number of the length of the sequence. So what is the cost? The cost will be extra memory. So that memory amount is of size 2 multiplied by number of tokens, multiplied by number of layers, multiplied by number of KV heads, and then KV dimensions, 2 as in key-end value. So it's using extra memory to speed up the calculation. That is what KV cache is for. So then we come to a set of new concepts. So KV cache is very important in speeding up the models, the transformer-based models. But it's very it consumes a lot of memory, and it often becomes the bottleneck, especially when the sequence is longer and longer. So people are thinking, okay, can we do something about it? And then people start thinking about MQA and GQA. So MQA is the multi-query attention, and GQA is the group query attention. Again, please take a look at my Transformer series about attention if you're interested. This is a graph of how the multi-head attention, the classical version of it, how it works. So basically, each query token corresponds to a keys and values a matrix, and they're gonna do matrix multiplication. And we cache keys and values, and it's gonna consume memory. So if we want to cut that memory, a intuition is, can we group some of them? Like, can we merge 2 into 1 or 3 into 1? Or in the extreme, merge everything into 1, right? So GQA, MQA is doing that, and MQA is on a pretty extreme, like all the query head corresponds to one key and one value, and group query is in the middle. It tries to merge, and the merging mechanism actually each model is different. I remember Llama is probably doing 2 to 1. Forget about all the other models, but group query attention is somewhat in the middle. So yeah, as I said here, MQA is to share a single key and a single value head across all the query heads. So obviously it can significantly reduce the memory usage, but as you can imagine, if you previously you are using 8 matrix to represent a attention, and now you only use 1, there's going to be a lot of information loss, right? So it's going to impact the quality and negatively impact the accuracy of attention. So GQA is in between. It tries to share only by a group of query heads, not all queries. So the quality impact is less, and you still have some memory gain. Okay, so I'm not going to talk about MQA. I think GQA is probably more useful. So GQA pros, the quality is GQA has quality closer to MHA by finding a better balance, and speed. So GQA maintains a speed comparable to MQA, which is faster than the classical multi-head attention, right? By reducing the KV cache memory. So if you reduce the KV cache memory, it also reduces the computational complexity. Like there will be less matrix multiplications. And then it also have lower memory usage. So it's more suitable for large scale models with like memory constraints, which is what DeepSeek do. So cons. So when you compare GQA with the classical MQA, like obviously there will still be quality loss, right? The balance between speed and quality is still a challenge. So you need to be really smart on the grouping strategy to minimize the quality loss. And then there's the group division, right? So the division and management of groups adds to the complexity of the GQA implementation. So that's another one, complexity of implementation. So this too is similar. And then because you introduce more like extra complexity, you introduce more hyperparameters. So you have to tune more parameters, and it's very it has huge impact on models' performance and efficiency. Okay, so before I dive into the multi-head latent attention, I want to talk a little bit about another concept, which is rotary position encoding rope. Previously in my transformer series, I talk a little on the absolute position encoding, which is here. And if you need more details, take a look at my other videos. Anyhow, so in today's modern architecture, this rope rotary position encoding is more popular. For the reasons, I'm going to start a separate series, separate episode, I mean, to explain why rotary position encoding is better than absolute ones. But now you can just consider like most of the models is actually using rope as position encoding right now. And the idea behind it is you try to apply a rotation matrix which transforms gxy to this new gxy. So you preserve the length of the original vector, but then the position, the angle of it is changed. And how to like efficiently calculate this is by introducing this 2-2-2 matrix. And this is the rope formula, and M is the position, by the way. Okay, so let's take a look into DeepSeek's MLA implementation. On the left part, this is a decoder-only architecture. So it's different from the previous like encoder-decoder transformer architecture. This is what right now like GPT uses. It's also what DeepSeek uses. And in the feed-forward network, I already talked about it in the first episode. They use MOE to replace the feed-forward network, and in DeepSeek's case, they have shared expert and they have routed expert. So this time I want to talk about the attention part. This is what's also very important. So let's zoom into this MLA module. So DeepSeek uses a low rank attention mechanism they call like MLA, which projects the keys and values into a shared low rank space. So this equates to reducing the sum of the dimensions of the query key and value vectors. So what it does, it compresses the original key value and query to to a lower dimension, similar, like it's the same concept of what GQA would do. So as you can see, this is the original input, and then after some after some compression matrix, it will compress the input to a lower dimension matrix. So one thing is, rope isn't like simply preserved by the low rank compression. So the mathematical calculation is more complex, so I won't talk too much details. But so that's why DeepSeek uses a pretty smart approach. They have a single query pair that doesn't have the compression matrix, and these queries and keys are added directly, like summing to the decompressed queries and keys without like position embedding. So as you can see, this one have rope and this one have rope, but there are some matrices that doesn't have rope, so they don't have any position encoding, and we concatenate the position encoding with rope and without rope, and do a dot product to get a multi-head attention. So this is how they solve the rope problem, but in fact, with some additional calculation, rope could be combined with MLA directly. So let's say you have this, this W, big W is the compression matrix. So you can find a new matrix that that conforms to this condition. So using this new smaller W matrix, it will ensure that rope matrices like commute with the low rank compression matrices, since like the rope matrices are composed of 2 to 2 blocks on the diagonal. So actually there are other ways to do MLA, I would imagine, but this is how DeepSeek decided to do, and it has been working pretty good. So they find ways to reduce the KV cache by compressing the cached elements dimension, and they find a smart way to include position encoding into it without hurting the ability to do KV cache, and that's why they make their attention mechanism so cheap, and it doesn't hurt the quality that much, so the quality is still pretty good. So now we have gone through DeepSeek MOE. We have also gone through the multi-head latent attention. This is two of the main reasons why DeepSeek is cheap and good. There are other reasons, especially in infrastructures. So I might do extra episodes to cover those. Hope you find this useful. Thank you.